Hello. In this segment, we will consider section 3.5, the chain rule. So, chain rule is an additional formula to evaluate derivatives of functions. In particular, it's the formula to evaluate derivative of a composition of two functions. And in this section, we will derive that formula in a simple way without much detail, and we will consider a number of examples of how to use the formula. So our general approach in calculus is to break a complex function into a combination of elementary functions for which differentiation formulas are known. Differentiation laws allow us to do that. They allow us to take the derivative that is applied in front of the function and to distribute it through the function so that the derivative goes to every simple element of that function. The resulting expression is usually pretty complex, and each step of that process is guided by the differentiation laws. So what differentiation laws we already discussed? We discussed the sum law, the difference law, the product law, and the quotient law of differentiation, the product rule and the quotient rule of differentiation. So these rules are consequences of different ways of how you can combine two functions to build a new function. So two functions can be added together to form a new function, or two functions can be multiplied together to form a new function. And for each action that allows to combine function, we have a differentiation law, differentiation rule. So today we will consider a differentiation rule that works on a composition of two functions. Composition is the last operation in which two functions can be combined that we will consider in this segment. So the formula for the derivative of a composition of two functions is known as the chain rule. And we will find out that between the sum rule, the difference rule, the product rule, the quotient rule, and the chain rule, derivative of any function given in a closed form can be evaluated. And the closed form means that the function is given as a formula using a finite combination of sine, cosine, tangent, cotangent, square roots, different kinds of exponents, exponential, and any sorts of known function that you can come across. So as long as the function is combined out of those, and there's only a finite number of pieces of those, chain rule, product rule, quotient rule, sum and difference rule can break that construction down, which is a very, very powerful result. Okay, so we will start by essentially looking at, we will go through the material of the section, and I will make some comments where, it's important I fill in some gaps. So hopefully you will be learning something interesting today. So just to start the discussion, let's take a look at this example. So we have an example of a function, square root, and underneath the square root is x squared plus 1. Now, it is a little bit of an art, but after looking at this function for some time, you can notice that this function is a composition of two simpler functions. The first function is square root of a variable u, and the second function is x squared plus 1. If we take this composition of two functions, so-called g of x, which is another way to say that we will take function f, and instead of the variable u, we will substitute g of x, then we will obtain the function of this example. So what does it tell us? It tells us that the function in question is formed by taking a composition of two other functions. And the other two functions are apparently simpler. You can take a derivative of the first one, you can take a derivative of the second one. So today we will consider a formula known as the chain rule that allows us to combine these derivatives to find derivative of the composition. So the statement of the theorem is given over here. That's the chain rule. Let's read it. Suppose we have a differentiable function g, and it's differentiable at x, and function f is also differentiable, and in particular will be differentiable at a point given by the value of g of x, and we will discuss why this is important. Then we can consider the composition of f of g of x, and it turns out that that function, that composition, will be differentiable at x, and the derivative will be given by the following formula. So let me recap this formula. So we have composition of two functions, f applied on top of g of x, and we would like to evaluate a derivative of that composition with respect to x. So I can put prime, but what this prime means, it means d by dx. And that derivative can be evaluated in the following fashion. So first, we need to evaluate derivative of the function f taken alone, and we will substitute g of x into the result, and then we will multiply by derivative of function g. Now, very, very interesting, but this derivative is related to derivative of function f with respect to its variable. The theorem doesn't really say here, but if we say that f is a function of u and u is equal to g of x, then that derivative is actually a derivative with respect to u. A derivative with respect to u of function f of u. But notice that what we do, we first evaluate that derivative and then substitute function g of x instead of the variable u. And variable g of x is just d by dx of g of x. That's pretty straightforward. So one of the things that we wanted to emphasize is that f has to be differentiable at g of x. It looks fancy, and what does it really mean? Well, it's a bookkeeping. If we look at function f of u, we may expect that at some point the derivative may exist, and some points the derivatives may not exist. For that theorem to work, we need existence of the derivative for the function f at a very, very particular point. Where that g of x is. We want the derivative exists exactly where that at that value. When we substitute x inside g, we get a value, and we want f to be differentiable at that value. So hence that condition. It's a bookkeeping. All right, so one last thing before we go with the proof. We often see something known as Leibniz notation, the dy by dx notation. These are very, very powerful notations, but you have to use them carefully. So in particular, if we think of y as the function of f of u, and if we make a composition, so we'll plug the g of x here, well, you could also think of that variable y as a function of variable x. And that's something that you have to be careful with. In the first case, function is variable of u, and the second case is variable of x. But these are slightly different functions. We had a substitution here. Well, nevertheless, with this new notation, there you can talk about derivative of variable of y with respect to x over here. On the other hand, if we look at the right-hand side, we notice that we have these two terms. The first term is f prime evaluated on g of x. Well, what is f prime? Well, that is derivative of y with respect to variable u, the original form. So here we go. That's the second piece. And let me change the color again. Now the last portion is derivative of g with respect to x, which is plainly du by dx using, say, this substitution. So we formally can restate the chain rule like so. dy by dx equals dy by du times du by dx. And the Leibniz notations are very useful for remembering the chain rule. So let me write it down here. So dy by dx is equal to dy by du times du by dx. In a very, very formal way, you can see that the du in the right-hand side can cancel, and we would get dy by dx on the left-hand side. Except that, of course, we don't cancel those du's. The meaning of it is not a fraction, it's a indivisible symbol, the derivative. However, it is good to remember that if you have dy, which is a function of u, and du that is a function of x, then making dy by du times dy by dx essentially results in the chain rule for the composition where y is dependent on x. All right, but this is a side comment. Some people appreciate the simplicity of the Leibniz notation, and it does help them to remember how the chain rule works. So it is yours. So what we're going to do next, we're going to go over the chain rule. So let us spend a few minutes and let us show how the chain rule can be obtained from very, very simple considerations. So what we will do a naive proof. And the meaning of naive is that it's not mathematically sound. And I will tell you exactly where it's not mathematically sound. Nevertheless, it's very instructive to see how the proof works so that you know where the formula comes from. Knowing when the formula comes from helps many people to remember the formula better. So we will start from assuming that function f is differentiable and function g is differentiable. All of the conditions of the chain rule are satisfied, and we will consider a composition of the two functions. And what we would like to do, we would like to evaluate the derivative of that composition. And the starting point is to use the limit definition of the derivative, which is always applies for the derivative. So every formula that we developed so far has limit definition behind it. So there we go. I will use the following limit definition of the derivative. Limit as t goes to x of. Here I will put f of g of t, and here I will put f of g of x, and in the denominator I put t minus x. Now, if you are wondering where this came from, well, it's just a definition of derivative. And let me use a different letter. I will say h of x equals limit as t goes to x of h of t minus h of x divided by t minus x. So I'm sure you remember this formula by now, and replacing h with the composition, that's what we get in the numerator. Okay, so that's a good start, but what do we do next? Well, we do the following. Let me show you a trick. We will do a trick. We will assume for a moment that g of t minus g of x is not equal to 0. Now, it is a strong assumption, and this is why this proof is naive. There is a mathematical flaw here. We cannot guarantee that g of t minus g of x will not be equal to 0. The claim is that you can prove the theorem without this assumption, but it would be more involved and less intuitive. So today we just want to focus on the main idea, and we will use that assumption to show the main idea, and we will show where that special form of the chain rule is appearing. So very well, we will assume for a moment that this difference is not zero, and we will multiply and divide our fraction by that difference. So we will start by f of g of t minus f of g of x. We will put it in a parenthesis here, and here we have our t minus x, and we will multiply by the following fraction, g of t minus g of x, and we will divide by g of t minus g of x. Very well. Because we assume g of t is now equal to g of x, we can do it. We have a fraction that is equal to 1. So, very well. So what do we do next? Well, then, the purpose of introducing this g of t and g of x was to take the original expression and massage it into a different expression. Let me show you which one. So I will group these two terms. I'll take that, and I'll group it with that. And then I'll group the other two terms together. So let's see. So after we group the two terms, we will have f of g of t minus f of g of x. And let me erase that parenthesis because there's too many parentheses, already hard to read. And it will be divided by g of t minus g of x. And then the second one, I will have g of t minus g of x divided by t minus x. And now we start to see where it's all headed. Notice that this expression over here is very, very similar to this expression over here. And it's not a coincidence. It was intentional. So what we're going to do, we're going to jump on that hint and we're going to do the next step. So assuming that limit can be worked out, we formally distribute limit of a product on each of the multiples. So, and we will replace that expression with limit as t goes to x of f of g of t minus f of g of x divided by g of t minus g of x times limit as t goes to x of g of t minus g of x divided by t minus x. Notice that the second term here looks very familiar. What is it? Well, it is exactly the definition of the derivative of function g at point x. Well, very interesting. Looks like we've got portion of the chain rule completed. Now, however, what do we do with the front expression, the first term? So here we will do something else. So we will denote u to be equal g of x, all right, and w to be equal g of t. If we do that, then see what we're going to get. So I'm not going to touch that limit for a moment, but I will be working it. I will continue working on it. But with just this substitution, every time I see g of t, I will put w. And every time I see g of x, I will put u. And every time I see g of t, I'll put w. And every time I see g of x, I'll put u. That looks almost like the definition of derivative, except that limit is not quite what we want to have. What we want to have is that w goes to u. Then it's a definition of the derivative, with u being the g of x. But what we have is t to x. But here we use a mathematical fact. If g of x is differentiable, then g of x is continuous. So the function has to be continuous if it is differentiable. Now what that means, as t goes to x, g of t will have to go to g of x. But g of t is nothing but w, and g of x is nothing but u. And what it means that we can replace limit as t goes to x with all of these things in mind. We can replace that limit with a limit w goes to u. F of w minus f of u divided by w minus u. And I will copy the g prime x because it didn't go anywhere. Well, now I hope we all recognize the derivative of function f in the first term. That's nothing but f prime u. And we have f prime u times g prime x. This is why sometimes when people describe the chain rule, they say the chain rule is just the product of the derivatives of the two functions. So composition product derivative of a composition is equal to the product of derivatives, with one little caveat that u is not an independent variable. U is equal of g of x. So we actually will have f prime evaluated on g of x multiplied by g prime x. So that completes the proof of the chain rule in an intuitive way. In the end of the section in the textbook, there is a rigorous proof using differentials, which is the proof that's used in most of the advanced textbooks. And you are very welcome to go and look through this proof. But I wanted to bring up this proof because it shows how the formula is appearing. And it's a very, very simple several steps. So please review and hopefully you will remember. It will help. So please review and hopefully it will help you remember the chain rule. Let us now consider a few examples of using the chain rule. In the beginning, we will go slow, but eventually we will accelerate and start skipping some steps. But in the beginning, I would like to go very slowly and break down the problem into smaller steps. So just to recap, the derivative of the composition of f of g of x, and I will use the prime here, is equal to the derivative of function f evaluated on g of x times the derivative of function g. So I would like to evaluate derivative of the following function, square root of 1 minus 2x. And the first step I would like to do, I would like to see it as a composition of two functions. Now, a lot of people have difficulties with starting to see a function as a composition of two simpler functions. I recognize that it is difficult. Actually, I think this process is an art compared to a procedure. In the procedure, you will be given a collection of steps, and once you go through the collection of steps, then you will have the answer. Now, art, on the other way, is something that requires inspiration, and there is no strict rules how to go, but you will have to find that way. That would probably be a unique way, and it will not be applied anywhere else. So in this case, I consider this process of looking at the function and breaking it down as a composition of two functions being more of an art than a procedure. And one of the problems with looking at a function and breaking it into composition is that there's infinitely many ways to do it. Now, not every way will be suitable for our final goal, finding the derivative of the function. Like certain ways maybe will not be very helpful. Nevertheless, with a little bit of practice, I hope you guys will find an approach. You will start seeing the composition. And the rule of thumb is that you like to keep it simple, so it should help you solve the problem. If it makes more complicated than when you started with, that's a good indication of error, and you can go back and do it again. And of course, it's a trial and error. You just give it a try. If it doesn't work, try something else. So now I've seen a lot of examples like this, so it's a little bit easier for me. What I see here, I see a composition of two functions. Their function f, and let me use variable u here because I'll try to follow the notation of the book. But eventually, everything will be a function of x because it's somewhat easier to think of. Now, the second function is g of x equals 1 minus 2x. And the claim is that when you compute the composition of two functions, you will get the original function back. Let me show you, a very naive way to compute composition of two functions if you haven't done it in a while. So a good way to do it is to start by comping the function. And notice how I give myself a little bit of room here. So u has a little bit of room here, and the square root has a little bit of room. This is why. I would like to compute a composition. So composition results of substituting u equals g of x. So every time I see u, I will remove u and I will put g of x. Now that's over here, but over here I will substitute the actual expression for g of x. Well, I can do it in two steps if you wish. So it's going to be square root, and instead of g of x, I'll put 1 minus 2x. So, long story short, it looks like we've got our breaking correctly, so we can proceed with using the chain rule. For the chain rule, we will need derivatives of f and derivative of g. So derivative of f is 1 over 2 root u. Notice that that derivative is with respect to variable u, the one that defines the function f. Now, on the other hand, derivative of the function g is derivative with respect to x. The chain rule doesn't highlight it, but please keep in mind the f prime is derivative with respect to the variable that defines function f, and g prime is derivative with respect to the variable that defines function g. So in the first case it was u, in the second case it is x, and derivative of function g is -2. That's actually a pretty simple derivative. So here we go. Now we start putting it together. So derivative of square root 1 minus 2x is equal to the derivative of f of g of x is equal to the chain rule. And now we start the substitution. Instead of g of x, we'll just put -2 because that's what it is. And instead of f prime of g of x, we will put 1 over 2 square root. But we don't put u here because we don't need f prime of u. We need f prime of g of x. So we will put g of x in here. So -2 cancels, and we have -1 over instead of g of x, we need to put 1 minus 2x. So that would be the final answer. So for now, we do all of these intermediate steps, but in the future, you can skip most of them, if not all but the last one, and you will be able to move through this problem significantly faster. Okay, let's try another one. Y equals tangent of pi times x. it's a pretty straightforward decomposition. The function f would be tangent u, and function g of x would be pi times x. In this case, pi is a constant. It looks fancy, but you just think it's a number multiplied by x. So, very good. Let's find the derivatives. The derivative of f is 1 over cosine squared u, or some of you will say cosecant squared u, which is the same thing. And g prime x is pi. It's a constant. So now it's time to write the whole derivative. So derivative of tangent of pi x, let me put it in parentheses so that we see it a little bit clearly. So derivative with respect to x is equal to derivative with respect to x of f of g of x. According to the chain rule, we'll need to take derivative of f and evaluate it on g of x and multiply it by the derivative of g of x. Continuing, g of x is very simple. It is pi, just a constant. So we will multiply by pi over here. And for f prime of g of x, we need to start with 1 over cosine squared. But instead of the variable u, we will substitute the function g of x over here. So it's going to be pi x. So the final expression is pi divided by cosine squared pi x, or pi cosecant squared pi x. Let's consider another one before we go and consider slightly more interesting problems. So again, we would like to find derivative of a function, and we are looking at the function, an exponential function, natural exponent, e raised to the power square root of x. So the suggested breaking is f of u would be the exponential, and g of x would be the square root of x. Very good. So let's just go ahead and compute the derivatives. The derivative of natural exponent is itself, so that's going to be pretty straightforward. And the derivative of square root x is 1 over 2 square root x. Very good. So now we're ready to put everything together. Derivative of the composite function e raised to square root x is the derivative of the composition of f of g of x. And according to the chain rule, we'll have derivative of f evaluated on g of x multiplied by derivative of g of x. So derivative of g of x is easy. We will copy it right here, 1 over 2 root x. And derivative of f evaluated on g of x is as follows. We will start with exponential raised to exponent. But instead of exponent u over here, we will make a substitution. We will substitute g of x. So f prime evaluated on g of x reads e to the square root x. As you can see, it's a substitution. Instead of the variable, we plug g of x. Notice that this is the first term. That's the second term. Very well. So we can simplify it just a little bit. I'm not sure if there is any simplification, but we can write it as a fraction. E raised to square root x divided by 2 square root x. Perhaps it looks a little bit better than the original formula. Now, one last comment. There's a certain slang that we often use when we apply a chain rule. The function f is often called the outside function, and function g is the inside. And this link is related to the composition, f of g of x. So g goes on the inside, f goes on the outside. So identifying the outside function is a crucial step in applying the chain rule. If you identify the correct outside function, you are one step ahead right there. So hopefully these two examples that we considered will help you get started on more interesting problems. So now we'll make a quick comment that chain rule can be combined with other rules. And some of these combinations become a shortcut formulas. They're not independent formulas, but if they are met frequently enough, then you can use it as a standalone formula. So, for example, if you look at the formula sine of g of x, and we don't know what g of x is, but the derivative with respect to x will always have that form. So derivative of the outside function, the sine, so derivative of the sine is cosine, and here will be g of x, and multiplied by g prime x. So the chain rule allows us to see these patterns, and you can even write a special formula. If it's a composition of sine and another function, then that's the formula to use. However, sine is not the most useful one. However, sine is not the most frequently used one. What is frequently used is the power rule. Power rule combined with the chain rule. So here is the power rule over here. And if we have a composition of a power function and a function g, meaning that I'll raise function g to degree n, then the derivative will be n times function g of x raised to degree n minus 1 multiplied by the derivative of function g. So that formula, given right over here at the bottom, is known as the generalized power rule. Again, it's not an independent formula, and to derive that formula, we needed the chain rule and the power rule combined. So as long as you remember power rule and you remember chain rule, you can rediscover that formula pretty quickly. Nevertheless, it is a shortcut, and oftentimes you will see this formula in a list of differentiation formulas. We will now go ahead and solve a few more examples. Now we have more complex functions, and the chain rule will be applied in combination with other rules. So we will evaluate a few more derivatives. We will try to speed things up and try to break things down into simpler steps, but maybe not as many details as we did in the beginning. So hopefully that would be sufficient amount of detail. So we would like to find the derivative of function y with respect to x. And that means we need to take derivative with respect to x of this fraction. 2 sine 2x cosine 2x. And the first formula to use is the quotient rule. Just in case we need to remember quotient rule, this is it is. Derivative of a fraction is derivative of f multiplied by g minus f multiplied by the derivative of g and divided by g squared. So the first thing to use here is the quotient rule. And according to the quotient rule, we will have d by dx of 2 sine squared x multiplied by cosine of 2x minus 2 sine squared x multiplied by the derivative of cosine of 2x and divided. Okay, let me put parenthesis here so that we see what derivative is applied to. And in the denominator, we will have cosine of 2x, everything squared. Now, the thing is that with these examples, they very quickly grow in size and complexity. It is highly recommended to keep computations neat because it will save you a lot of errors and mistakes. And also, it is recommended to do computations on the side. So, for example, this derivative, we can evaluate it on the side. Like we will just look at the derivative of 2 sine squared x. 2 is a constant. We can bring it outside of the derivative. So we have derivative of sine squared x. And sine squared x is the same as taking sine of x and taking the square. Well, we are having a case of generalized power rule, and the outside function is x squared, and the derivative of x squared is 2x. So we will start, okay, so there's 2 that's coming from here, and then there will be 2, but instead of 2x, I will have a substitution. Instead of x, I'll put sine of x, so it will be 2 sine of x. And then we need to multiply by the derivative of sine x. Continuing, 2 and 2 combines into 4. Sine x just stays itself, and derivative of sine x is cosine x. Well, interestingly enough, using the double formulas, we can wrap it. We can wrap that function as 2 sine 2x. I'm not sure it's going to be useful in any way, but we can put it that way. So either expression, this one or that one, will be accepted for full credit. Okay, so we took care of that first term. Let's take care of the other second term. So I will have d by dx of cosine of 2x. So let's see which one is the outside function, which one is the inside function. Well, it looks like the outside function is cosine of, let's say, u, and derivative of cosine u is negative sine u. So when we do the chain rule, okay, let me write the chain rule here just so that it's in front of our eyes. Derivative of f of g of x prime is f prime evaluated on g of x times g prime x times g prime x, and here f is the cosine and g would be the 2x. So here we go. When we take the derivative of the cosine is negative sine, so we'll have negative sine. However, instead of u, we will substitute g of x, which is 2x. And then we will take 2x and differentiate. So negative sine of 2x times 2. Now it's time to continue our original problem. So we'll put the denominator and copy cosine of 2x squared. In the numerator, instead of derivative of 2 sine squared x, we will write 2 sine of 2x, which will be multiplied by the cosine of 2x, and then we will subtract 2 sine squared x multiplied by the derivative of cosine of 2x is 2 well, negative sine of 2x. That's what we have in here. So let's continue this expression. It can be simplified just a little bit. The factors of 2 can be combined into 4. Then we'll have sine squared x. And the minus will be combined with this first minus, and it'll become a plus times sine 2x. Well, I guess there's a possibility of even further simplification here, but maybe not worth it. So sine squared x could be replaced with the cosine of double angle. There is a formula for that, but I'm not sure if it will be nice simplification, but you're welcome to try it. So I would like just to stop here. In general, we don't spend a lot of time simplifying these formulas. If the goal is just to evaluate the derivative, then we don't expect a lot of simplifications. This derivative will come out arbitrarily complex, and there's not much hope to simplify it to a nice form. It is important to focus to complete all the steps correct, and as long as the steps are correct, you will get full credit. There's one exclusion from this rule. There's one particular topic when we'll do graphing of functions using calculus. In that case, it is good to simplify, but that's the only case. In all other cases, we can leave derivative as is. We could probably spend some time, maybe we'll find some very interesting way to simplify it, but it looks like it's not worth the effort. So I will stop over here. Okay, so let's do this one last example. We would like to differentiate the product of two terms. The first term is 2x minus 5 raised to degree 4. And the second term is 8x squared minus 5 raised to degree negative 3. Well, the first rule to apply here is the product rule. And after the product rule is applied, we will have derivative of 2x minus 5 to the fourth multiplied by 8x squared minus 5 to the negative third plus 2x minus 5 raised to the fourth multiplied by the derivative of 8x squared minus 5 raised to negative third. So again, as in previous example, the expression quickly grows and becomes more and more complex. So it is good to put it put some computation on the side. So here we go. Let's evaluate this derivative. d by dx of 2x minus 5 raised to 4. Now, a good way to remember the chain rule is the following. So we can think of composition of function as nested dolls. And we can think of taking derivative as applying to derivative to this nesting dolls. So in particular, we can start with applying the derivative to the most outside function. And when we apply it, we're thinking like opening that nesting doll. And what is inside that nesting doll is the function g. So we'll take that function g, we'll put it over here and hit it with the derivative as well. So that's another easy way to remember the chain rule. And here, instead of function f of u, we'll have u raised to degree 4. And instead of function g of x, we will have 2x minus 5. So let's get started. So first we apply the derivative to function f. We will have 4u raised to degree 3. Except I don't really need u. What I need the function g here. So it's going to be 2x minus 5. Then I will take 2x minus 5 over here and differentiate. Let's do it again. So 4 multiplied by 2x minus 5 raised to degree 3. That's the result. That's the f prime evaluated on g. And the derivative of 2x minus 5 is 2. So the first term simplifies to 8 multiplied by 2x minus 5 cubed. So hopefully you will like that way of differentiating. Again, if you're not comfortable with this way, you can use the way we did it in the very, very beginning. But as we do more and more examples, naturally you try to go faster, so you develop some sort of shortcuts. This is one of the possible shortcuts, but you can develop your own shortcut. So please welcome. It's a nice creative process. So now let us focus on the second term. And we will start with the derivative of quantity 8x squared minus 5, everything raised to negative 3. Now, in this case, the outside function is u raised to negative 3. The inside function is 8x squared minus 5. And we will start by taking derivative of the outside function, negative 3 something raised to negative 4. And that something is the function g of x, so let me put it here. And now we take that function and differentiate. So just to emphasize, the outside function is f, and this whole first term is matching to this part. And that second term is matching to that part. Notice that I'm not done. I'm still having a derivative here. I still have to evaluate it. But breaking it into these steps helps me keep track of things and also speed things up. So now I need to evaluate the derivative of 8x squared minus 5. Well, that's a very simple derivative. Let me finish counting here. I'm sorry. So the derivative of 8x squared minus 5 is going to be 16x, and that's what it is. Overall, we have negative 48x multiplied by, parenthesis, 8x squared minus 5 raised to negative 4. That is the second term. And then we just go ahead and substitute these terms into the final expression. So instead of the first derivative, we have 8 2x minus 5 raised to degree 3 multiplied by 8x squared minus 5 raised to degree negative 3. And here, okay, I notice that this minus will bounce up front. So instead of plus, I will put minus, and I will have 2x minus 5 raised to 4. And from the second derivative up to a minus, I will have 48x 8x squared minus 5 raised to negative 4. And we would not simplify any further because I don't think any good simplification would result. We would just leave that expression as is. So let us consider another interesting application of chain rule. Chain rule allows us to evaluate derivatives of exponential function for any base. So far we only considered exponential function with the base e, the so-called natural exponents. And they are, of course, very, very important functions, their derivative is equal to itself. And that is the only function that has that property. So as a result, this function is extremely important in ordinary differential equations and anything that involves integration, because going from derivative to the function is so simple. So we know how to differentiate e to the x, but we don't know how to differentiate b to the x. So we don't have a formula yet. Well, one of the things that we can notice that we have certain rules about exponentials. So logarithmic and exponentials are inverse functions to each other. So we can take this exponential function, b raised to x, and we can use laws of exponents. So in particular, b is equal e raised to natural logarithm of b. That's an identity that we're supposed to discuss in pre-calculus. And what we can do, we can replace b with e to the natural log of b. And then everything is raised to degree x. Now, then we have laws of exponents. So in particular, a raised to r and everything raised to s is the same as a raised to r times s. So we can use that law of exponent to simplify to e natural log of b, and let me put it in parentheses, times x, which is the formula over here. B to the x is the same as to say e raised to natural log b times x. Now we can try to use that formula to derive the derivative of exponential function for an arbitrary base. So instead of b raised to x, we will put exponential of natural log b multiplied by x, and we will take a derivative. In this case, derivative is taken with respect to x. According to the chain rule, we have the chain rule, and the outside function is e to the u, and the inside function is constant. Natural log b looks fancy, but it's just a constant multiplied by x. So derivative of f of u is e to the u, and derivative of u is equal to natural log of b, the constant. I will not put it in parentheses anymore, so I will leave it as is. According to the chain rule, we will have derivative of the most outside function, which is e raised to u, except instead of u, we will substitute natural log b multiplied by x, and then we'll need to multiply, we'll need to take that whole expression over here and bring it over here, natural log b times x, and differentiate. So e to the natural log b times x times the derivative of this expression is natural log b, because natural log b is a constant, and constant can be pulled out from inside of the derivative, and derivative of x is equal to 1. So summarizing, so it's going to be natural log b multiplied by e raised to natural log b times x. Now we're almost done. The last step is to notice that e raised to natural log b times x is nothing but b raised to x. Hence, we can write our final formula. Natural log b times b raised to x. So what we just did, we established the following rule. To differentiate the exponential function with general exponent, we will have b raised to x multiplied by natural log b. So here we go. We have an additional formula, and you can add it to the collection of all of the other differentiation formulas, and we can use it in some examples in the following. Exponential functions often appear in population dynamics. So in particular, when you're trying to compute a viral load, a base, exponential relations, and equations that lead to exponential formulas. So in particular, here we have example 9 from the textbook, and it shows a formula for the viral load. It's not immediately clear, but the way that function looks like is certain constant a times certain constant b raised to exponent t. And that is an exponential function times a constant. So suppose measurements were done on a patient with HIV, and this patient was given a treatment, a certain antiviral, and it was observed that the viral load behaved in the following fashion using this constant. So what we need to find the derivative at t equals t and interpret it. Okay, so let's start by finding the derivative. So let me just do it on the level of letters because it's a little bit easier for me to handle. But if you would like, you can keep numbers. So for me, A is 96.39785 and B is 0.818656. So, but fundamentally, it's just one constant times an exponential function. So let's take a derivative of that. According to the rules of differentiation, constant can be pulled out from the differentiation. So we have this, and the derivative for exponential function with arbitrary base is given right here in the box. So it is going to be b raised to t multiplied by natural log b. So substituting the specific values, instead of a, we'll put 9639785 multiplied by, then we have 0.818656 raised to t, and multiplied by natural log of 0.818656. Let me use computational software Desmos to put the numbers in. So what are we looking for? And let me maybe leave a little bit more room for this notebook rather than Desmos. So let me introduce a function. Let me call it h of t, because I don't have any good ideas how to call v prime. So I'll call it h, but it is v prime. And this function will be given by 96.39785 multiplied by, and here we have 0.818656, everything raised into exponent t, and multiplied by natural log of 0.818656 and parentheses. Very good. So Desmos made a graph of our function, but we probably don't need to see that graph. We just need to evaluate the value at 10. So here we come. V prime at 10 comes about negative 2.60801. Okay, how many digits I have here? 1, 2, 3, 4, 5, 6. So let's get one more digit. So that will be rounded up, will be 5. And that is the viral derivative of the viral load at t equals, I'm assuming, 10 hours. Yeah, we need to go back and see what is 1.4. I would assume t is hours. And viral load is the number of concentration of viruses, I suppose. So again, sorry, I didn't look back. And the derivative turns out to be negative, which is good. That means that number or concentration of viruses, or viral load, is decreasing. It's changing with a negative. That means there's less of them. With approximately negative 2.6 concentration, less concentration in the next hour. Okay, that's my interpretation, but let's see what the book has to say. Well, first of all, they got the negative 2.6, so looks like we were good here. And they say, oh, it's a 10 days, like T equals 10 days. Apparently, no, T is a day, not an hour. Sorry, that's what it means. It's days. So in the next day. So the book says that it will decrease at the rate of about 2.6 RNA copies per milliliter per day. So that was the concentration. Next thing that we would like to consider is applying the chain rule several times concurrently. This is the case when we take derivative of a function that has composition inside a composition inside a composition. So in that case, we have a long chain of functions, and we'll have several applications of chain rule. Now, there's different ways to approach it. I would like to introduce my favorite approach, which is taking one chain rule at a time. So in these examples, we have multiple compositions. So in particular, I can see that I will have function f, and it is evaluated on function g, which is in turn evaluated on function h. And if you would like to see, then function f would be the sine of u, and function g would be the tangent of w, and function h would be 2x. When you combine all three, you will get the original function back. So the way to apply the chain rule to multiple compositions is to do one chain rule at a time. So we apply chain rule to the most outside function. Namely, so f is the most outside function, so we'll take derivative of f, and we will evaluate it on g of h of x, and then we will take that g of h of x, we will put it over here, and hit it with a derivative. And that's one step of the process. What's going to happen next? Next, we're going to copy the first part because the first part is done. And we're applying the chain rule to this second term. And, well, in this case, we already know the result. It's going to be g evaluated on h of x times h prime x. So applying one chain rule at a time and keeping the rest as the whole thing allow us to do longer chains. Let's take a look at this example. We would like to evaluate derivative of sine of tangent of 2x. The most outside function is sine. Derivative of sine is cosine. But the argument of cosine will be tangent of 2x. And then we will take that argument, like we take our nesting doll, apply the derivative to it, open it, take what's inside, put it next, and differentiate. So we will take our tangent of 2x and hit it with the derivative. We are not done yet because now we take a derivative of the second term.
The first term we just copy. That's pretty straightforward. But the second term will have cosecant squared. But for the variable, I'll put 2x, and then I take that 2x, take it out, and differentiate. So the final answer is cosine of tangent of 2x times cosecant squared of 2x times 2. Let's do it again on this example. I have, oh my god, that's an example where it's very difficult to see what is happening. So we will have to put some parentheses in here. So 2 is raised to the degree 3 raised to the degree x squared. So to put, like, after I put the parentheses, we can tell which is raised into which degree. And we would like to apply the derivative with respect to x to this composition. So in this case, I see the most outside function is 2 raised to u. Then would be 3 raised to w. Then there would be x squared. So again, we have a case of 3 functions folded into each other. So, okay, we'll start with the most outside function. And it would be natural log of 2 multiplied by 2 raised into that entire thing. So 3 raised to x squared. And then we need to take 3 raised to x squared and differentiate. Okay, so we copy everything over. You'll start with the natural log 2, which is here. And then the first term is done. It's 2 raised to degree 3 raised to x squared. And now we deal with the derivative of 3 raised to x squared. So derivative of 3 raised to something is natural log 3 times 3 raised to something, which is x squared. And then we need to take that x squared. Okay, let me try again. We'll take that x squared and differentiate. So one more step. Let me take the natural log 2 and natural log 3 and put them together. You don't really need this parenthesis, but I just put parentheses and we clearly see what's multiplied by what. So it will be 2 raised to degree 3 raised to x squared. Let's just copy. And 3 raised to x squared, I also just copy. And the derivative of x squared is 2x. So finally, we'll have 2 natural log 2, natural log 3. We cannot really combine them well, so we'll just keep them like that. Times 2 raised to 3 raised to x squared. And multiply by 3 raised to x squared. Multiply by x. Okay, that solves this problem. Okay, and to conclude with, well, I don't know, we can do more, right? It's a video, we can. Okay, let's consider another example. So I would like to take a derivative of cube root of 1 plus x times x plus 3. And we'll like to take the derivative with respect to x. The most outside function is cube root. The derivative of cube root is 1/3 quantity raised to the exponent of -2/3. And inside the quantity goes 1 plus x multiplied by square root of x plus 3. And then we need to take that expression on the inside, put it on the outside, and differentiate. Continue. First, I copy the first term in the product. There's nothing to do here. It just sits like that. And the derivative of the second one, well, derivative of 1 will be 0. And then we'll have to use the product rule. First, there will be derivative of x times the root, x plus 3, plus x times the derivative of root of x plus 3. Continue. So a lot of copying in these problems, but try not to make mistakes when you copy. Unfortunately, these expressions get long, but this is part of your training, being able to handle complicated formulas. So 0 is 0, so I'm not going to write it, but derivative of x is 1. So the first term will be pretty much equal to square root x plus 3. Now, then it will be x multiplied by. So I will just go ahead and evaluate derivative of x plus 3 on the side. So here I have a composition of two functions. The outside function is square root of w, and the inside function, so that would be f of w, and g of x is x plus 3. Taking the derivative of the outside function, we'll have 1 over 2 square root, but for the variable inside the root, I'll put x plus 3, and then we'll need to take that x plus 3 and differentiate. So the first term I am copying, but the second term, the derivative is equal to 1. So for the derivative of square root of x plus 3, we will write 1 over 2 root of x plus 3, and we will close parentheses. And that completes this problem. And let us consider one additional example of differentiating the following function. So we have x squared multiplied by square root, and inside the square root we have 1 plus root x. We would like to evaluate the derivative with respect to x. So the first rule to apply is the product rule. We will have derivative of x squared times that root, which I copy, plus x squared multiplied by the derivative of the root. So derivative of squared is 2x, so the first term we more or less obtain. And for the second term, I suggest that we pull it aside and evaluate it on a separate spot. So we have here a composition of two functions. The most outside function is the square root. So derivative of the square root is 1 over 2 square root. And inside that square root goes 1 plus square root x, because that is what's inside the root. And then we'll have to take that 1 plus square root x and differentiate. So one more step. First, let me copy 2 multiplied by square root 1 plus square root x. And the derivative of this expression will be 0 plus 1 over 2 root x. So long story short, we will have something like this. 4 square root 1 plus root x times root x. You could distribute the root inside, but it's not worth it. These expressions are allowed to look ugly. We don't have to try to make it nice unless, as I mentioned earlier, unless we are solving a problem for graphing. Then you will benefit from simplifying the derivative. Okay, so here's our final answer, and we can stop right here. And just in case, I would like to look at a couple more problems. So we have an example. Find an equation of the tangent line to the curve at the given point. So we have a function, sine x plus sine squared x, and we would like to find the equation of the tangent line to this graph, to this curve at the point 0, 0. Now, just to recap, if we have a point x0, f of x0, then the tangent line has the following equation. Y minus f of x0 equals f prime x0, x minus x0. So in this case, x0 equals 0. F of x0, which is sine 0 plus sine squared of 0, that's also 0. So we know most of the values for that formula right there on the spot. The only thing that we don't know is f prime evaluated at x0. So let us start with evaluating the f prime, which is evaluating the derivative of sine x plus sine squared x. So the first term gives us cosine x, and the second term, we have to use a chain rule. The most outside function is the square. So applying the chain rule in the second term, we have 2 times sine x, and then we need to take sine x and differentiate, obtain cosine x. So here's the expression for the derivative. Cosine x plus 2 sine x cosine x. But that's a derivative in any point, but we need a specific one, x0, which is, in our case, 0. So we just need to do a substitution here. Now, sine 0 is 0, so that term goes away, but cosine 0 is 1. So f prime is apparently 1. So f prime of x0 is 1. So what we have, y equals 1 times x, or y equals x. So interestingly enough, y equals x is a tangent line to this curve at 0, 0. Okay, let's look at the problem 45. So 45 looks very confusing, but it is all about using the chain rule. So let's take a look. Suppose capital F of x is a composition of these two functions, f and g. And we have information about f and derivative of f and a couple of points. And we have information about g and derivative of g. Our goal is to find derivative of f at x equals 5. So let us start by finding an expression for f prime. Well, it is literally the application of the chain rule to this composition. So it would be derivative of f evaluated on g of x times derivative of. Now we need to evaluate that derivative at a very specific place at x equals 5. So we just go ahead and start substituting. So in particular, g prime at 5, well, apparently it's given to us. It is equal to 6. Okay, let me just go ahead and start substitution. So f prime evaluated at 5, according to my formula, would be f prime evaluated of g of 5 times g prime of 5. Well, g prime 5 at 5 is equal to 6. G of 5, on the other hand, is -2 according to this piece of information. So when I need to evaluate f prime of g of 5, I am actually looking at f prime evaluated at -2. We do have that piece of information. F prime at -2 is equal to 4. So here we go. That's 4. So the first term is 4. The second term is 6. Altogether, 24. And to conclude, let us look at a problem that is not standard, but it is fairly interesting and it's not particularly hard. So we need to find the 50th derivative of y equals cosine 2x. It is probably hard to guess that formula out, so a good place to start is to evaluate a few derivatives. So in particular, let's start with the first derivative. According to the chain rule, we have to take derivative of the outside function. We're going to get negative sine. But on the inside, we'll have 2x, and then we'll need to take 2x and differentiate. And that simplifies to sine of 2x times 2. So negative 2 sine of 2x. All right, very good. So let's take a look at the second derivative of y. And I'm not sure why I'm writing this parenthesis. I don't really need that. So the second derivative of y is the derivative of the first derivative. So that would be derivative of negative 2 sine of 2x. Well, negative 2 is just a constant multiple, so we can bring it out. Okay, let me put derivative here. And derivative of sine of 2x we can evaluate using the chain rule. In particular, it will be cosine of 2x multiplied by the derivative of 2x, which is 2. To summarize, negative 2 squared cosine of 2x. Okay, moving on. So let's take another derivative. That would be the third derivative, which is the derivative of the second derivative. And we will write that second derivative, negative 2 squared, multiplied by cosine of 2x. And take a derivative of it. Negative 2 squared is a constant multiple. I can move it outside. And inside I have derivative of cosine of 2x. Well, we do know what that is. We've seen it before. So that is actually equal to, okay, let's put negative 2 raised to the degree 2. And, I'm writing here negative 2 to the degree 2, but please pay attention that order of operation tells me that first I raise to the exponent and then multiply by negative 1. So that negative 1 is not raised into second exponent. Okay, with that said, the derivative of cosine of 2x is negative 2 times sine of 2x, which combines to positive 2 cubed sine of 2x. And I guess to complete, maybe we should take one last derivative, the fourth derivative. I can use either Roman letters or I can use Arabic numbers in parentheses here. And the fourth derivative, which is the derivative of the third derivative, is derivative of 2 cubed of sine of 2x, right? And I'll have the 2 cubed, and derivative of sine we already have computed. It's going to be cosine of 2x times 2. So we will have 2 to the 4 of cosine of 2x. Now, we've made 4 derivatives. We took 4 derivatives, and we arrived pretty much where we started, except for the factor of 2 raised to the 4. So the claim is that when we get to the 8th derivative, we're going to have 2 to the 4. We're going to have 2 to the 4, that factor, and when we differentiate cosine of 2x, when we differentiate for additional times, we're going to get 2 to the 4 of cosine of 2x. So it would be something like this. I mean, how do I know it? Because constant, you can pull it from the derivative. So when you apply another 4 derivatives, you may as well just see what's happening here. We started with cosine 2x, and after 4 derivatives, it gained a factor of 2 to the 4. After another 4 derivatives, it gains another factor of 2 to the 4. So you will have 2 to the 8 cosine of 2x. So then I'm thinking, you know, making 4 steps is good, but it's even better to make 8 steps. So let's go to the 16th derivative. 16th derivative means 8 additional derivative. But I know what the 8 additional derivatives do. They just add another factor of 2 to the 8. All right, so altogether is 2 to the 16 of cosine of 2x. Well, we are almost done. Now, let me just make another leap. You know, I will want to do additional 16 derivatives. Now, you could continue by 8, but you'd have to do more steps, and I would like to go fast, right? So additional 16 will get me to the 32nd derivative. 32nd derivative, and they will result in additional 2 raised to 16 factor of cosine 2x. So 2 raised to 32 of cosine of 2x. Now, at this point, I cannot really double anymore because I'll bypass. My goal is 50. But I can do another 16 derivatives. So that will lend me to 48, which would be 2 raised to 32 times 2 raised to 16 cosine of 2x. So it's going to be 2 raised to 48 cosine of 2x. Okay, and from here, I just need 2 additional derivatives. Well, we actually can do it directly, or we can go up and we see what the 2 derivatives do. The 2 give the factor of negative 2 squared. So what we're going to have 2 raised to 48 multiplied by negative 2 squared times cosine. Is it cosine? Yes, it is. Cosine of 2x. So here we go. Negative 2 raised to 50 cosine 2x. I hope you had fun. It's a really interesting problem, and it's not particularly hard, but it requires you thinking outside of the box, so I hope you enjoyed it. Thank you very much. That concludes the segment for 3.5 chain rule. The next segment will be still section 3.5, but it will be connected to implicit differentiation and related to